And yeah, so the video from previous class should be on the website now, but it's a little annoying, so I'm trying to do this by streaming on YouTube, so the video will be automatically saved. But yeah, so if anyone know how you actually stream on YouTube, please come to the class, and that will be helpful. Anyway, so let's back to our actual teaching. So quadrant from last time, I think we are around, yeah. So last time we were talking about periodic discrete signal that looks like complex exponential, and there are quite a bit like periodic complex exponential for continuous function. Just change t into n, but there are several points that are different, mostly because you only have points at integer values. So if your frequency is too high, then your discrete values actually don't see the higher frequency. Okay. So the frequency is actually meaningful up to the range up to 2 pi. So you only care about frequency from 0 to 2 pi. If your frequency goes higher, then then your picture actually goes back to the same as the lower frequency one. Okay, then see from 0 to 2 pi here, and the highest frequency for discrete signal is at omega 0 equal to pi, and you can see the picture look like up down up down up down, and that's the highest frequency you can get on discrete signal. Okay. And this changes the fundamental period calculation for discrete signal too. So for continuous signal, the fundamental period is just, well, the fundamental frequency just this omega 0, and the fundamental period is just 2 pi divided by this omega 0. But for discrete signal, the period must be an integer. So the fundamental period is 2 pi divided by this omega 0 and times another integer. Okay. And sometimes it's not periodic at all. So your omega 0 need to be a rational multiple of 2 pi. So omega 0 is 2 pi times m divided by n. Then it's periodic. If it's not, then your discrete complex exponential is not periodic. Okay. And yeah, and this m divided by n, you can read your fundamental period here. If your m and n are coprime, then your n is your period. Okay. And so any question here? If not, then let's see example of all this. So yeah, so now we have our discrete signal that are complex exponential, but there are now 2 of them. Okay, so yeah, 2 complex exponential adding up to each other. So there's the j 2 pi divided by 3n and another j 3 pi divided by 4n. And the question is, what is the fundamental period of the first part, and what's the fundamental period of the second part, and if you add them together, what are the fundamental period? And yeah, so we are going to use this very soon. Actually, something similar. Okay. So I guess that's not read the if we don't read the word here. So the equation we are going to use is this. So your fundamental period is similar to what we write here, right? So if you move things around, or we got this earlier too. So we have this 1.58 says that your fundamental period is 2 pi divided by omega 0 and times some integer m. So now we have those 2 parts, and you can calculate what's 2 pi divided by omega 0. So omega 0 here for this part is 2 pi divided by 3, and so 2 pi divided by omega 0 is 3 here. And for this part, omega 0 is 3 pi divided by 4. And you calculate 2 pi divided by omega 0, that's a over 3. So they are both rational, that's really good. So we can calculate the period here, right? So this part is already an integer, so your m don't need to be anything, m can just be 1 and n equals 3. So this part has period 3, and this part you have a over 3. If you times 3, if you pick m equal to 3 here, then your big N can be 8. Okay, so the period of the first one is 3, the period of the second one is 8, and for the period of x of n, you want to be the common multiple of these, or both of them, so 3 and 8. So the period of everything is 24. Okay, so that's the solution to this question. And the book offers another way to do this. So it says it's simpler, but well, depends what you think. But it's kind of a dumber way. So if you don't go through this, and the other way to think about this is for this to be a period, you want 2 pi here, okay? Multiple of 2 pi here, okay? And the dumb way is just checking whether at which n this thing can be 2 pi up here, okay? So from here you see, can you have 2 pi divided by 3 times n equal to 2 pi? And the answer is yes if you pick n equal to 3. Okay. And that's how you find out that the first thing has small n equal to 3 as its period. And then you look at this part, you think, can 3 pi divided by 4 times something equal to 2 pi? Well, the answer is no. If you want that small n need to be a over 3, and it's not possible, and then you check 4 pi and you check 6 pi. So yeah, so that's basically the calculation we've done here, but I guess it's more intuitive. Yeah, and finally you check 6 pi, and you find out if small n is 8, then 3 pi divided by 4 times 8 equal to 6 pi. Okay, so so the period here is 8, and that will be periodic because the exponent here is 6 pi. And yeah, and finally you have 3 and 8, so the total period is 24. Okay. So any question for this example? Well, counting the period of discrete and complex exponentials. Not. Then yeah. And let's go to the final concept of this. So we had harmonically related periodic exponentials for a continuous time, and obviously we have the same concept for discrete time. So those are the periodic harmonic related. So once again, the harmonic related complex exponentials. Complex exponentials that all have a common period. So the common period here is big N. Yeah. So everything kind of will look like e to the j 2 pi divided by n 2 pi divided by big N times small n. Okay. And but there are more possibility than just j2 pi. So if you call this omega 0, then there are more possibility than just j omega 0 n, because yeah, because your complex exponentials can have smaller period. So yeah. So just like in continuous time, in discrete time you can put an integer multiple k here. Okay. So every psi k that is e to the j k 2 pi divided by big N times small n. The all function of this form for every k has a period of n, and the set of all of them are called harmonically related periodic exponential. Okay? And because of this so you see the omega here is k 2 pi divided by n, and remember that for discrete time signal, omega is only meaningful between 0 and 2 pi. So there are actually not infinite k that are meaningful here. So for example, if k is increased by a value of big N, then you see that you go through this complex calculation, should be exponent calculation. Then you see that the same as psi k of n. Okay. So actually there are only n of them, big N of those signals that are different to each other, because omega only go from 0 to omega only go from 0 to 2 pi, and they start with 2 pi divided by n, and you count it, and you see that there are only n different of them. So only n meaningful k, that is k from 0 to k to n minus 1. Okay. And so we will write all that. K equals 0, that's the constant function. K equal to 1. Then you have e to the j 2 pi n divided by big N, and equal to 2 4 pi n divided by n up to 2 pi n minus 1 small n divided by big N. So any question about harmonically related discrete time exponential? If not, okay, then we go to our next section. So so this is the end of discrete time exponentials. So this is the section about signals, and we are going to talk about two very important signals: unit impulse and the unit step function. Okay. So the concept of those two signals are actually quite easy. Not really how this, but a very big mistake over here is, or something you need to care about, is you need to remember the names here. Okay. So make sure you memorize the names, or sometimes in the text, in test or in homework, you will just not understand what the question is asking. So so remember the name unit impulse function, also the symbol delta of n or delta of t. Obviously this is for discrete time, this is for continuous time. Also unit step function, u of n and u of t. Okay. So you need to memorize the names. So help you memorize that, we're actually going to see what they are. So let's start with discrete time, because the continuous time definition is a little more complicated with some limits. Okay. So for discrete time, the unit step function and the unit impulse function are quite intuitive. So unit impulse function is one impulse at somewhere, or if you don't shift it, it is one impulse at 0. Okay. So you can see this is like a simplest function you can think of almost, other than constant function. So it's 0 everywhere, and they have a 1 at 0. Okay. And the unit step function a little more complicated, but also very simple. So it's 0 if for every n, let's say it's 0, and it's 1 for everything bigger than or equal to 0. Okay. So and now you can see the name makes sense. So it's an impulse because there is an impulse at 0 here, and it's a step because it like move up a step here, kind of like in a year later. Okay. So it steps 0 and move up a step to 1 up here, and this delta and the u you just need to remember. Okay. When you see delta, delta make a little more sense when you see continuous time, or if you have seen it. So in continuous time, this is a delta function, but this u u is for unit step. Anyway, you need to memorize the delta and the u. Okay, and yeah, that's a very basic version is delta of n and u of n, like this. And if you want to this be a little more useful, then you want to shift this around. Okay, so this goes back to what we do a few weeks ago. So if you have instead of delta of n, so if you shift your time variable here by n to n minus n0, then when n0 is bigger than 0, you are delaying the signal, so you are shifting this pulse here. Okay, hope you still remember this time shift. So yeah, so delta of n will have your impulse at 0 at n equal to 0, and delta of n minus n0 will have your impulse at n equal to n0. You can quickly check that when n equal to n0, then that's delta of 0, and that should be 1, and everything else should be 0. Okay, and similarly for unit step, you have u of n minus n0, and that just shifts your step starting from 0 to starting from n0. And obviously, if n0 is less than 0, then you shift from here. So, any question? The definition should be quite straightforward. Impulse and step. Okay, and yeah, then there are some interesting relations with them. They are so simple. They have some really nice property. So first is that the impulse function and the step function are closely related to each other. So the impulse function is kind of a differential of the step function. This is more clear when we go continuous time. But for here, you can see that the impulse function delta of n can be written as u of n minus u of n minus 1, shift over the u of n. Okay? Because so at 0, that's 1 minus 0, and you get 1 here. And for the left hand side, everything is 0 minus 0, so that's 0. And for every n that's bigger than 1, that's 1 minus 1, and that's 0. Okay? And so delta is kind of like a differential of u, and obviously you can turn this around and have your step function as the integration of delta. Okay? So yeah, now this is a bit confusing here. So yeah, so remember what this is like an integration. So it's delta of m here, and m is something you sum over, and you have n here. Okay, so you are sum up m up to n. Okay, and yeah, and if you picture this, you have you are summing over this m axis, and yeah, and you sum up to n. So if n is less than 0, your summation, you are only summing over all the 0 parts, so your summation is 0. And if your n is greater or is equal to 0, then you have sum past this impulse part, so your summation result will be 1. Okay, so we check that this formula is correct. And now, to get it a little more confusing, we do a change of variable. Okay, so this is like a standard integration where you have dummy variable being sum over, and this n is written in at the upper bound of your summation. But if we do a change of variable, we instead of summing over m, we summing over k equal to n minus m. Okay, and yeah, so m becomes n minus k. Okay, from here m is n minus k, and this upper bound and lower bound. So when m equal to n, k equal to 0 because k is n minus m, and when m equal to minus infinity, k obviously equal to minus infinity, plus infinity. Okay, So we have u of n equal to summation k from infinity to 0 delta of n minus k. So what we've done here is we pull the n. Remember we have n up in the upper bound here. So now our summation doesn't depend on n anymore. Our n is in our function. Okay. So we are summation in our functions. And yeah, and then we can move this around. So this is discretized summation. So from infinity to 0 is same as 0 to infinity. So we have u of n equal to summation k from 0 to infinity delta of n minus k. So that's another way to see u of n as a summation of delta of n. And I think there are two interpretations here. So an interpretation is you can write this as summation over k x-axis, and now your interval from 0 to infinity, and you can see your delta of n minus k. But I think the more fun way to see this is we go back here. Okay. So you see that u of n here is all those steps here, or all the. So u of n, look at this step, and it have a 1 at every n bigger or equal to 0. So you can think this as u of n equal to delta of n, which is this first spec here, and the delta of n minus 1, which is the second spec here, and delta of n minus 2, which is the third spec here, and then also summing over. Okay. So that's another interpretation. U of n as summation of delta of 0, delta of n minus 1, delta of n minus 2, etc. Okay. So yeah, we don't have a picture here, but hope you understand. So everyone, any question? Yeah. So that's another running sum of u of n. The bottom line is you can think u of n as a summation of delta of n. Okay, so this should be quite intuitive too. And yeah, so nice property of those. I guess this is only for delta function. So this is why one of the reasons why we want to talk about delta function is they can help us pick up details about different signals. So you have a signal x of n, and if you multiply it with your impulse function delta of n, and you found out that will pick up the signal at small n equal to 0, right? Because if you multiply this signal with this signal, you see that everything else except n equal to 0, it becomes 0 because you are multiplying 0, and at 0 that's x of 1 times x of 0. So at the end you also get the impulse function, and its height is x of n. Okay. And similarly, so this pick up the signal at small n equal to 0. If you want to pick up signal at small n equal to some n 0, you just multiply it with delta n minus n 0. Okay. So yeah, so here is the example of n 0 equal to 5. So delta n minus 5, look at this, it has a pulse at n equal to 5, and you multiply it with x of n, and you pick up x of 5 times delta of n minus 5. And this is called shifting or sampling property. Any question? If not, how much time do we left? Okay, so let's go back to the more confusing part, that is the continuous time impulse and the unit step function. And so their names and notations are basically the same. You still have unit impulse, they are still called unit impulse and unit step, and it's still written as delta and u, just with the bracket now become the parentheses. So you have the curly parentheses instead of the bracket, meaning that it's continuous time. Okay. Okay, so unit step function is very similar. Is 0 if the t is less than 0, and 1 if t is bigger than 1. And when t is exactly equal to 0 is kind of undefined. So there are many ways you can define this. Someone define it as 1/2, someone at 1, someone define it as 0, but doesn't matter in our application. We only for what do we do? U of t. Yeah, I don't think it matters what u of t at t was 0, but I guess I'll say u of 0 equal to 1/2, just for symmetry. Yeah, okay. Now the weird thing is the unit impulse function. So this is, mathematically speaking, this is not actually a function because it's undefined at t equal to 0, and that's actually important part. So we write it as as an arrow here, and this means that this thing has infinite height at t equal to 0. Okay, so how does this infinite height actually works? Is through a limit. So we are thinking this as something that delta function is something very high. So something very thin and very high, but that has finite area. Okay. So the definition of this whole thing is basically hinged on if you integrate through this spike, the integration will be 1. Okay. And because it is finite integration, you can also have it times some number, although infinity times k is still infinity. But if you integrate over k times the delta function, it will become k. Okay? Okay, that's a little change of order, but let's back to the basic definition of this thing. So we think so unit step function and unit impulse function in continuous time are both a little divergent, and we define them as the limiting of some more smooth function. Okay? So we think u of t as something that's 0 at or 0 side, and at some point delta become 1, and you connect like this. Okay? And if you take the limit of delta equal to 0, this thing becomes your step function u of t. Okay? And delta of t is actually defined as the differentiation of u of t. Okay? And yeah, so remember we have for discrete time we have the difference and the rounding sum, and now this is kind of taking us a definition of delta function and the unit step. So for the delta function is now a differentiation of unit step function, and if you take differential of this thing, so at this part is horizontal, so it's 0, and this part is also 0. So only non-zero part is this slope here, and you can easily see that the slope here is 1 over delta, and you only have it's only from 0 to delta. So you see that the area of this rectangle is 1. Okay. And if you take the limit that your delta goes to 0, then your height 1 over delta will go to infinity, and this width goes to 0, but the area will stay the same all the time. The area is 1, and that's very important. And I guess something we can say is also, you might argue that why are we taking this very specific form of approximation? And indeed, you can take all kinds of different form here, like more curly connection here, or you push instead of 0 to delta, you have minus delta to 0. Okay? But they will all converge to similar things, and the only property we need is this integration and differentiation between unit step and the delta function. Yeah. So it should be the next slide. Yeah. So the most important property of the delta function is actually this relationship. So if you integrate over a delta function, then you get 1. Okay. It's 0 everywhere, but once your integration region is cross over your delta function, the integral is 1. Okay. And also the reverse of this thing is that if you take derivative of a unit state function, and you will get a delta function. So any question? No? Yeah. Okay. Then we do one parallel of what do we do in the discrete case. So remember, in discrete case, when you do this integral, we do a change of variable to push this t into your function, and then we can do a similar thing here. So instead of integrating over tau, we're integrating over sigma, that's t minus tau. And so then tau becomes t minus sigma, and t is basically a constant here. So d tau is minus d sigma, and you can check the upper bound, lower bound should be 0 and infinity. Then flip it around, and u is now integration 0 to infinity delta of t minus sigma d sigma. But now it's continuous time, so you cannot really line up your delta function. So you really need to think this, check this as integration on sigma, and from 0 to infinity, and this thing is 0 if your t is smaller than 0, and it's 1 if your t is bigger than 1. Because your delta function, when t is smaller than 0, your impulse is not in your range of integration, and when t is bigger than 0, then it's in the range of integration, so this is just 1. So any question? Not? Okay. Then we go to our shifting property. Okay? And just like this case, the unit impulse function can be used to sample your arbitrary signal by multiplying them. And we kind of justify this once again with our small delta approximation of our signal. So if you multiply our signal with with this delta of delta function, okay, you multiply those two, and you see that it's 0 everywhere except that this very thin region. Okay, and as your big delta goes to 0, then if your x of t is reasonably smooth here, then this will become a constant function. Okay, so this part just looks like a constant function that has value x of t because it is very thin region. And and so the result of this multiplying x of t to delta of t will be x of 0 times delta of t. Okay, on this part, and obviously also true on other part because they are just 0. Okay, so this is so you can see that with this impulse function, you can also pick up the value of your signal by multiplying your signal with this impulse. So x of t times delta of t is x of 0 times delta of t, and you can also pick up x at different values, say t0, by multiplying it with delta of t minus t0. Yeah. So x of t times delta of t minus t0 is x of t0 times delta of t minus t0. Question? Yeah. So shifting property is just like the discrete time. but we justify this with this limiting behavior of delta sub delta. So we think true delta function as this delta sub delta as big delta goes to 0. Okay, and yeah, just another reminder. Shifting property x of t times delta t minus t0, x of t0 delta of t minus t0, and this is how we justify it. And yeah, finally we have this example that asking that if we have a function that looks like this, and what is its derivative? Okay? The function is 0 until it's at t equal to 1, then it becomes 2, then it jumps to -1, and it jumps to 1. Okay. And yeah, so what is derivative? And we'll keep using this relation that delta function is a derivative of unit step function. Because this thing kind of looks like a unit step function, but instead of just one step, you have one step going up, another step going down, and another step going up. Okay. And yeah, and we just have our answer here. So here we are. So first we see that this thing is this function is constant basically everywhere except of those three jumps, right? There is jump at 1 and jump at 2 and jump at 4. Now what are the derivative here? So the jumps look like the jumps in a unit step function, and when you take a derivative of a unit step function, you get a delta function, and that's exactly what happened. So first here you have a unit step function jump from 0 to 2, so that's basically twice the unit step function, and so you take a derivative, you should get twice the twice of delta function. Okay, and the second step, you have a unit step function that has a jump of 2 to -1, so a jump of -3. So when you take a derivative, that should have -3 times the delta function. And finally, you have a +2 here, so you get another +2 of delta function here. Yeah. So yeah, so this is our answer. You have 3 delta function here, correspond to these 3 jumps. And the delta function are multiplied by some number that correspond to the magnitude of those jumps. And we can check our answers. Let's see. So we have a lot of words to say what we said. So I guess we can also check our answer. So we said this picture is the derivative of this picture. So if we do integration, we should get the back sensing. So yeah, so we integrate from we should integrate from -infinity, but it's okay. So we can integrate from well, it's all 0 here and it corresponds to 0, so that's okay. And so we integrate from 0 here, and we integrate over this function. So it's all 0 until we hit this t equal to 1. Okay, and when we have t between 0, small t between 1 and 2, then you integrate over this delta function times 2, so your whole value should be 2. Okay, then you integrate over this -3, and that's when your t is between 2 and 4, and then you are integrating over this spike and this spike, so you get a 2 here and a -3 here, so you get a -1. And finally you integrate over the third spike, and so you have all 3 valued integrator, so that's 2 - 3 + 2, and that'll give you a +1. Okay, so yeah, so you check this integration also works. So this is really a differential of the first function. And finally, we can write this in more algebraic way. Okay? So you can write this function as sum of 3-state function. So the first state function starting at t equal to 1 and has height 2. Then you minus another state function starting at t equal to 2 and with magnitude minus 3. And then finally, state function at t equal to 4 is plus 2. Okay, so think. Oh, question?
Is it possible that the changes happen in like 1.5?
At 1.5, sure. You mean small t equal to 1.5?
I mean the changes happening like from 2 to minus 1. That happens in 1.5. The point 1.5.
The point. You mean at time 1.5? Sure, you can happen. Huh? So you mean let me try to draw this. Are you saying can we have like the function going here like this? Yeah. Then you will just change the 2 here instead of 2 here you have 1.5, right? Yeah. So if you instead of a 2 you have 1.5, then you will just then this spike here will be placed here. Yeah. So those values don't need to be integer. It can be any real number, it should be fine. Also the height don't need to be like 2 and minus 1, you can be like 3.14 and yeah. The writing will get ugly, but it should totally works. Okay? Yeah, okay, let's erase this. Yeah. So yeah, as you can see from the equation here, so you have some number, those numbers are totally changeable, and those 2 minus 3, 2 and 3 changeable. And anyway, you write down your function as sum of unit steps. Then you do differentiation, then it's clear that you can just do differentiation one by one, and all those unit steps become delta function. Okay. So you have 3 delta functions, and t equal to 1, t equal to 2, t equal to 4. Any question? Not. We are. What time is it? Let me check. How do I? We have 5 minutes. Do we want to? So we are catching up this year. I guess we can talk a little about the system, but not too much. So yeah, let's talk first 2 sides here. Yeah. So just as a reminder, so we talked about this on the first class. So what is the system? So we have talked about signals. So and the signals are basically functions, and they are discrete function, continuous time function. And the system is something weird, something you don't see in math class that much. So it's something that change a signal to another signal. And yeah, we are kind of thinking like an engineer here. So there will be input signal, and your system will change it to output signal. And there are many many examples of systems. So the most relevant one here is signal processing. Say you have a video here and you want to censor it, so you add some mosaic on it, and that's a signal processing. Or you have a video is too large and you want to compress it, that's another system. And we'll also have weird example where we have operation system on our computer. Anyway, yeah, lots of things you can view as systems. And yeah, so I guess our system is a little restricted. So we have continuous time system and discrete time system. So continuous time system will map a continuous time signal to another continuous time signal. And discrete time system will map a discrete time system to another discrete time signal. And I guess we don't have something crossover. Okay? And yeah. So our system don't change the domain of our signals. Range the signal. And most of the time we'll think this as 1D signal, although there are also systems for 2D signal. But anyway, so that's continuous time system and the discrete time system. Yeah, and we'll write it like this. So input signal to output signal, input signal to output signal. And we want to talk about this just quickly. And yeah, so as we see this example in our intro also. So example of a system is this RC circuit. And so you have a driving voltage here and a resistance and a capacitor in this circuit. And this is a very engineering system where your input signal is the voltage here, and there are several things you can think of as the output signal. And for now, we think the output signal is the voltage over your capacitor. And then you can do physics and solve the differential equation. And let's skip that. We don't care about physics for now that much. So yeah, so there is a current over here, and current is the differential of the current is the differential of voltage here. Then you can write down the differential equation, and at the end you find out that your system is satisfied by this weird relationship. Okay, so your output signal, we write this as y. You need to satisfy this dy dt plus ay equal to b times x of t. Okay, and yeah, so this is a system, and you can see that sometimes what's the output signal is not so straightforward. Okay, you can be written implicitly as the differential equation. So your input signal is this x of t here, and output signal is y of t here, and your system behaves like this. And if you want to get to know what's the output signal y of t, you need to solve this differential equation. Okay. And yeah, I think that's about time. And so for next class, we will talk a lot about systems. There are lots of properties about systems that we'll talk about, and we should be able to finish the first chapter next time, I think. Question? Not, let's stop here. Okay. Let me stop recording.